So we'll talk about different matching techniques, phasing lines, and they threw in a question about a power divider. So one of the main reasons to match the antenna to the feed line is to reduce the SWR. One of the reasons you care about SWR, well, one is most radios can only compensate for up to 3-to-1. And a lot of the external antenna tuners kind of limit you to a 3-to-1 SWR. The higher the SWR, the higher the standing wave that you're going to get, and the more power that you're going to lose in the transmission line. So when you send a signal out and part of it gets reflected back, I mean, you've lost part of that signal on the way to the antenna, depending on what the loss is. Say it was 1 dB. So you lost the dB of signal getting to the antenna. If you get half of it reflected back, you're going to lose another dB of that half on the way back, which is adding to the heating of the feed line. So, you get power heating from both directions, and then it gets reflected back again. Okay. So you get multiple hops, each one less power, more dissipated in the feed line. So you can get a lot of heating on the transmission line itself if you got a high SWR. There's a formula for SWR where it's the reflection coefficient, which is that funny Greek sign. Not sure what you call that one. Maybe it's tau. I think it's tau. Yeah, tau beta pi, yeah. Where it's the reflected voltage divided by the forward voltage. That ratio is the reflection coefficient. And the SWR is the ratio of 1 plus the magnitude of the reflection coefficient divided by 1 minus the magnitude. It's easier just to do the ratio of the impedances. It's approximately the same thing. So what parameter describes the interaction of a load and transmission line? Okay. One of the matches is a hairpin match. So it lets us match very low impedances to a 50 ohm coax. You can directly feed a Yagi because they're down in the 20, 25, maybe 30 ohms. It's not like the gamma because you have to have the driven element isolated from the boom to use this type of match. And it requires that the driven element be capacitive, which means what? That it's going to be shorter than its required length for resonance. Remember we talked about that before. It's capacitive on the lower side of resonance. It's inductive on the higher side. Now, this is a typical example, and you've got this loop connected to it. There's calculators that will tell you how to come up with these two numbers. I don't know that the size of the wire makes a big difference in this case. and also the spacing between the elements, the minimum. And that seems to be fairly typical, anywhere from a half inch to maybe as much as an inch separation. Yeah.
Would you get RF arcing across that?
With high enough power,
So there would be a.
but
power
remember,
limitation.
you're going to have the same problem in your feed line, especially if you're using a type N connector. Type N connectors are nice, but they also have half of the breakdown voltage or arc over voltage of a PL259. Because if you look at how they're made, the spacing between the center conductor and that little shield in the connector, it's much closer together than you see on the 259. I think they arc around 3,000 volts, and it's like 1,500 volts for an N. So half an inch, which would be 12 millimeters, I think it'd be much more volt. It's like 70,000 volts per inch, I think.
Is that millimeters?
Those are millimeters, yeah. Be an awful big loop if it was inches.
Well, then that's point.
No. Oops.
Got that in mind.
Did you read it?
No, but I saw it.
So what Yagi-driven element feed point impedance is required to use a beta or hairpin matching system? Which matching system for Yagi antennas requires the driven element to be insulated from the boom? Of the choices, gamma matches. So we can match unbalanced directly to the antenna. This is one where the driven element can be electrically connected to the boom, doesn't have to be insulated. So we feed the shield to the center, and then the center conductor goes through that little adjustable capacitor and a sliding clamp to compensate for any inductance that's in that matching network. It's also how they typically feed like broadcast towers, where the tower itself for AM radio is the antenna. So they just go directly to the base of the tower and feed it at that point with a gamma match. There's more details on actually how you can make it and the size of the tube and the center conductor, which you strip out of some coax and can slide it in and out of the tube, or slide the tube over it rather. And then the shorting bar where you put that. Seems kind of complicated, but yeah, I'll make one someday to try it. When an antenna matching system matches coax cable to an antenna by connecting the shield to the center of the antenna and the conductor a fraction of a wavelength to one side, what do you call it?
You call it alpha?
What's the purpose of the series capacitor in a gamma match?
Bravo.
Yep. Which of the following is used to shunt feed a grounded tower at its base?
Charles.
Stub matches, where we use a section of transmission line in parallel with the feed line. So depending on whether I take that section of line and short the end or leave it open will determine what kind of reactance it has. So by adjusting the length of it and whether it's shorted or open, I can make it whatever reactance I need to compensate for the antenna reactance, which is where you would use a Smith chart. Or you go online and they have Smith chart calculators. You just plug in the numbers and it does it for you.
Sounds better.
Yeah. This is kind of showing us a stub where one's open, one's shorted. And, you have to figure out the length of it and how far it is from the feed point itself. So what matching system uses a short length of transmission line connected in parallel with the feed line at or near the feed point? A quarter wave transformer. If we use a quarter wave length of transmission line, electrically quarter wave, I can use that as a transformer. And one of the applications, if I've got an antenna that says, say it's around 100 ohms, and I want to feed it with 50 ohms, if I put a quarter wave section of 75 ohm cable in series, then I'm going to get a match of 50 to 100 ohms. You look very skeptical. You do that by, it turns out you can use this formula. So the resulting or the required impedance to do that match between Z1 and Z2 is the square root of the product of Z1 and Z2. So if Z1 is 50 and Z2 is 100, and I multiply them together and take the square root, what do you think it comes out to? 72 ohms. I did that in my head. You testing me? That's what, like 5,000 square root? Or 50,000? 5,000. Okay, so which of these transmission line impedances would be suitable for constructing a quarter wave Q section for matching a 100 ohm feed point to a 50 ohm transmission line? Because they don't make 72 ohm. Did you get it yet?
I came up with 21.
That's wrong.
Yeah, I know.
You can also use pieces of coaxial cable as a phasing line. And we do that in order to, change the radiation pattern so I can make it directional, where I feed it at 90 degrees or 180 degrees out of phase. So what's the purpose of using multiple driven elements connected through phasing lines? Okay, and a Wilkinson divider. You ever seen one of those? Apparently, it's a little bit different than your old TV splitter, which would take 75 ohms in and you got two 75s out. This is usually used at UHF, where it's 50 ohms in and it's 50 ohms out. It's split and it just splits it. And it's just actually a couple well-made little inductors in there and a shunt resistor so that it looks like 50 ohms on the input and both of the outputs look like 50 ohms.
How much loss do you get?
I don't know. I assume you get a bit. So what is the use for a Wilkinson divider?
FCC likes straws.
Let's see, a delta match. Oh, I left it in there because um, they deleted the question. I don't know why I like delta match, where you separate your feed point to where you get 50 ohms or whatever, 75 ohms, whatever you're trying to match. In other words, you get the distance is a fractional wavelength, so you get the amount of impedance difference between the 2 points. Kind of like doing the match on the tower. It's the same sort of deal where you're shorted and in a certain distance away, it's 50 ohms. And typically, and it's one of those cases where you don't have to have your lines separated. You're just picking 2 points on there where there's a 50 ohm difference in impedance between the 2 points. Well, in this case, it's 600. So depends on what you're trying to match. So we talked about reflection coefficient, hairpin matches, gamma matches, stub matches, quarter wave transformer matches, phasing lines, and Wilkinson dividers.